So thank you so much. And the first three people there were my PhD students, are all postdocs at various places. And Sharanya is now faculty at Bangalore. And Axel and Anwar are my constant collaborators for all the stuff that I do today. What I'm going to talk about is, summary, is that you have in the formation of galaxies and galaxy clusters, various processes which are slightly, maybe not something which all cosmologists worry about, but it's something which is firstly very interesting, and then it's also something which you have to explain. And the first statement which I want to make is that the universe is magnetized, and I hope that you all get magnetized eventually in this, even if you are not at present. And you can see this from various things from our Earth. We are sitting on a magnet, which is like a dipole and very coherent magnetic fields, to the sun, which has this solar cycle of 11 years, to nearby galaxies, to high redshift galaxies, which have all microgauss type strength magnetic fields, coherent on some kiloparsec scales. For example, I'll show that, to plasma and galaxy clusters, to perhaps the intergalactic medium even in the voids, which is very tentative and very iffy evidence from gamma ray astronomy. And something which is common to all these systems is turbulence. And turbulence arises from different sources. And I want to talk a little bit about the turbulence and dynamos as applicable to maybe galaxy clusters and young galaxies, and also something which is slightly more complicated conceptually, is what is called a large-scale turbulent dynamo, which probably is responsible for all the coherent magnetic fields that we see in stars and galaxies. I will not talk about primordial magnetic fields, although there are very interesting works by many people, some of them in the audience, which if you really are interested, you can look at a review of mine written about a couple of years back in Reports on Progress in Physics. This is a very introductory article for students who are wanting to get magnetized very recently in a volume to celebrate the 125th anniversary of Subha, who is very famous, of course, in astrophysics. And long time back, Axel and I wrote a physics report. So just to give you a picture, when I once wrote a paper and I had no figures in the paper, then the referee said, hey, a figure is worth 1,000 words. Then I put a figure, but then I didn't have those 1,000 words because it was a PRL kind of stuff. Of course, I have a counter to that. An equation is worth 1,000 pictures. But I'm going to show you some pictures. For example, this is the nearby galaxy M51. And you can see this coherent, what is shown here is radio contours of synchrotron emission. And these lines here represent the polarization orientation. You can see nice ordered type stuff. You, of course, have to see the Faraday rotation to know whether the field is coming in or out. But basically, you have large-scale fields in nearby disk galaxies which are coherent on scales of tens of kiloparsecs. And what is shown in this part is a corresponding kind of image for a galaxy cluster, not polarized, of course, because polarization is very weak in the synchrotron emission. The colored stuff is X-ray emission, and the contours are contours of synchrotron emission from the GMRT, and that's why I'm showing this, because it's our own GMRT. And on these two sides is the other way of probing magnetic fields in extragalactic universe through Faraday rotation. This is an old plot from Tracy Clark and company of Faraday rotation through a bunch of clusters. And far away from the core, you see very little residual Faraday rotation. As you go towards the centers of clusters, you pick up Faraday rotation, which indicates also microgauss kind of strength fields, which have got coherent scales of tens of kiloparsec. And there's a statistical evidence for such coherent fields in high redshift galaxies by an old paper now by Bernay. And you see magnesium-2 absorption systems. If you have one of them along the line of sight, they show an excess Faraday rotation. And so basically, it looks as if that galaxies, galaxy clusters are all magnetized at some level. And it's interesting to ask what is the role of evolving turbulence, magnetic fields, and one thing which I have not mentioned so far, cosmic rays, during structure formation. So I'm not going to answer this question. I'm going to tell you how we think probably the first magnetic fields arose in the universe. Of course, the first turbulence in galaxies, we know the supernova stir the interstellar medium all the time. But even before supernova come on, just the formation of galaxies and clusters, which involves mergers of hierarchical clustering, will induce turbulent motions in the system. So what does it mean? And this is just an advertising slide. Should we think about magnetic fields? I'm sure that people are aware of the various contexts in our interstellar medium where everything is governed by fields, star formation, jets, various accretion processes, ejection processes, confinement of cosmic rays, outflows. A lot of things are governed by magnetic field, and I've just listed some of them. One point which I would like to mention is that people are all interested in galaxy clusters. If you ask what is the mean free path for charged particle in a galaxy cluster plasma due to Coulomb collisions at some sound speed and some density, it's about 5 kiloparsecs. So this is a pretty large scale. So you're thinking of galaxy clusters as a fluid, but before you think of it as a fluid, you should understand that it's a very highly collision-less system if you think just of Coulomb collisions. And there's a lot of plasma physics effects which is involved in making it collisional enough to make it a fluid. And that itself would be interesting, and it governs various processes, physical processes like thermal conduction, viscosity, and resistivity in galaxy clusters. And so it's interesting to think about magnetic fields in all these contexts, and the only reason I'm thinking about it is just fun, that's all. None of these. Now, how are magnetic fields maintained in various astrophysical systems? And the idea is that people often think that astrophysical systems are so large scale that they're highly conducting. So if you dump some field from somewhere, they just remain there forever because the conductivity is so high, currents don't get dissipated over Hubble times. And this is a slightly wrong notion, because once you have a field which is strong enough and it's structured on some scale, so there's a curl to the field, and so there's a current. If there's a current and a field, there's a force, Lorentz force. And the force will push on the fluid. If the fluid is highly viscous, it will get dissipated by just viscosity. If it's not so viscous, it will generate turbulence to smaller and smaller scales and get dissipated. So you cannot just leave magnetic fields by themselves and let it be there forever. You have to constantly maintain it. And the way that we think of maintaining fields is by a very simple law which you learn in school called electromagnetic induction, Faraday's law, that you say that if you have a curl to an electric field, we learn it the other way around. If you change the flux through a loop, you generate a current. Now, the MHT guys look at this differently. If you have a curl to the electric field, you can change the magnetic field. So it's just the other way of looking at it. And so you go about asking where are there curls to electric fields? And this is Ohm's law. If you have motion in a magnetic field, that motion can produce, in a good conductor, an electric field in the frame, in the lab frame, which has got a curl. And this is the basic equation called the induction equation. It says, of course, that you need magnetic field to maintain the field. So you need some initial source for the field, and that initial source for the field is called a battery effect. And there are very interesting simple physical phenomena which generate very small fields, and then you need to amplify them in some way. So you need initial seed field which is got by a battery, and you need to amplify these fields to produce observed fields, and these phenomena is called a dynamo, and that needs kinetic to magnetic energy conversion. The simplest form of dynamos arises if you have a turbulent fluid in a highly conducting medium, if you have turbulence in a highly conducting medium. What turbulence does is that if you have turbulent motions, you have two fluid parcels, they typically random walk, and they random walk away from each other in a typical realization. Now, if you attach magnetic flux to these two fluid parcels, and magnetic flux is supposed to be frozen very much in a conducting fluid, so if magnetic flux is magnetic field times the area, let's say, of some tube through which it's going through. You conserve magnetic flux. You conserve mass. Rho into A into the length of this flux tube is constant. You divide these two. B by rho is proportional to L. As you lengthen these flux tubes, you conserve the volume. They get squeezed in the perpendicular direction. You conserve magnetic flux. The magnetic field increases. So flux freezing plus random walk in a general turbulent medium can increase magnetic fields exponentially, because you increase it a bit, then you stretch it in some other direction, you keep multiplying. It's a multiplicative amplification, so which is exponential. And that's a simple form of dynamo. We call it the fluctuation dynamo. So random turbulence gives random stretching, flux freezing gives you fluctuation field growth. Of course, this is not going to do the kind of fields that you see in galaxies, which are very well ordered. But it's something where you automatically get, in the presence of turbulent medium, amplification of magnetic fields. And it will be highly intermittent, and one has to see how exactly, how this can explain observations, for example, the Faraday rotation in galaxy clusters. If you want to make large-scale field, you need some special stuff, for example, like helicity in your turbulence, like screw-like motions, and I'll give you a picture of that. It turns out the fluctuation dynamos grow fields in galaxies on the time scale of turbulent motions. Now, if you have supernovas stirring the medium, the largest turbulent eddies are about sizes of the biggest supernova remnants, tens of parsecs. Their velocities are typically 10 kilometers per second. So the turbulent eddy turnover time is about 10 to the 7 years, which is extremely small compared to galactic lifetime. So it's something which will amplify fields very easily for you. The large-scale field dynamo operates on a much smaller time scale, longer time scale, because it depends on rotation, stratification, etc. And so that takes a much longer time. And one also has to ask, how does these two things come to terms with each other? So these are some fluctuation dynamo simulations by, this bit is by Pallavi and this bit is by Sharanya. And where you take a periodic box, you stir the medium, and you can see that the field is fairly incoherent. And this is the magnetic spectra, which you start with very weak seed fields. This is a function of K. So these are small scales, these are large scales. Initially, because of this random stretching, the field goes to as small a scale as possible. Then as the field grows, it saturates with fairly more coherent fields, but still fairly random. So we wanted to ask, does this produce enough Faraday rotation to explain, for example, galaxy cluster observations? And so it turns out that it does, and these are studies which we have done, and it turns out it produces, like, if you had fields coherent on some scale, on the turbulent scale, and you shoot lines of sight through this kind of turbulent medium, you will expect a certain amount of Faraday rotation. This is the RMS strength. One line of sight you reduce by a factor of √3, you random walk through a length capital L, through a coherent scale of small l, you gain this much. And it turns out we get almost about 40% of that, of what you would ideally get in a turbulent medium. So it can, to some extent, explain observed Faraday rotation in galaxy clusters and in young galaxies. And remember that this comes about pretty fast, this fluctuation dynamo. I just thought I'll show you another interesting run by Sharanya a long time back on the first forming star, because the first star collapse itself could lead to turbulence and magnetic field generation. And this is something now which is pretty old, but this is also a place where you can get turbulence. And nowadays, people who are doing structure formation simulations have now finished various things that they were all interested in, and now they've started putting in magnetic fields, they've started putting in cosmic rays. These are some results from the next generation simulation, and there's a paper by Marinacci et al., I think always driven by Volker Springel. And if there was just flux freezing evolution, this is the strength of the field. They start with some seed field. And if there was just flux freezing evolution, this is the amount of amplification you will get as you form galaxy halos, the cores of galaxies. But you will find that you get a much larger amplification, and they're just beginning to resolve all the turbulence and the amplification due to due to the fluctuation dynamos. If you want coherent fields, of course, you have to do something more. And this is what we believe happens in galaxies. You have this galaxy rotating differentially. So if you have a field line, for example, which is radial, and you flux freeze it, it gets wound up to a toroidal field. This is one part of the story. This can only give you linear amplification, and it will not give you coherent fields, because if your radial field is random, you'll get toroidal fields in one way, winding in one way, and neighboring in radius will have toroidal field winding in the other way. So you will not get coherent fields. You need some helicity to turbulence, and we believe if you have helical turbulence, you take this toroidal field, make a loop, twist it a bit because of the helicity, and these can coherently add up to give you radial components. And you can do all this mathematically and find that you have a mean field dynamo which grows exponentially in time. I don't have great amount of time to say this, but this has various problems. One problem which I wanted to, So this is the recent simulations, again by the Volker Springer et al. Group, by Akamar, where they're trying to form a disk galaxy, and these are BZ, BR, and B phi. One would tend to think that there are coherent fields here, but you can see also that the color is different just in neighboring regions. You get lots of reversals. So what I feel is that they have now resolved turbulence. They are being able to follow to some extent the amplification of the field due to the general fluctuation dynamo, but still what happens to the large-scale dynamo is still not yet, I think, resolved in these kind of simulation. But I think it's good that this community, which is doing very detailed simulation of galaxy formation, are now beginning to put in the magnetic field effects in their simulations. One aspect which I wanted to discuss before leaving the subject is that what happens, there is this turbulence which is generating random fluctuation magnetic fields. Okay, 5 to questions. Okay, fine. And then there is this mean field dynamo which is trying to generate coherent magnetic fields. Now these are the two different time scales. Now you would imagine that if something is exponentially growing, let's say on 10 to the 7-year time scale, it will saturate pretty rapidly, and the Lorentz forces will come to stop all kinds of growth. So how does it affect the large-scale field generation? And this is something which we finally addressed through simulations. Again, these are simulations by Pallavi Bhatt. And what one sees is at initial times, when you start with a weak seed field, all the power is at large K. This is the fluctuation dynamo operating. And everything grows exponentially. And the scale, these simulations are periodic box simulations, where the stirring is on the scale of about 1/4 the scale of the box. That's the peak. The dashed lines here are kinetic energy spectra. The solid lines are magnetic energy spectra. And this 1/4 the scale of the box is where the kinetic energy peaks. The magnetic energy initially peaks at, let's say, K of about 70, which is much smaller scale of the box. But this grows, but as it grows, it doesn't kill the large-scale dynamo. Eventually what happens is, because the Lorentz force, the field orders itself. At final times, the field coherence reaches the scale of the box, provided you can get rid of something called magnetic helicity, which I had not had time to really talk about and make the whole thing work. And then you do find Lorentz forces have ordered the field on the scale of the box. So this is the same plot shown in a different way for different modes. Everything grows together, large scales and small scales. Scale larger than the scale of the stirring and scale smaller than the scale of the stirring grow together. But finally you end up with a large scale field dominating. So it's good news for us. We have also tried to see whether you can see signs of both these dynamos, the fluctuation dynamo and the mean field dynamo, by adding shear into the system and stirring with helical turbulence. And for the first time, we are able to see at least there is one stage of rapid growth due to the fluctuation dynamo, exponential growth. There's another exponential growth of the largest K equal to 1 mode due to the large scale dynamo. And we are beginning to see signs of both these dynamos. This is a logarithmic growth rate versus time initially it's large, dominated by the fluctuation dynamo. Then it is smaller, dominated by the large-scale dynamo. Finally, resistive, there's saturation here. There's almost no growth there. So where do we stand in all this? I wanted to convey to you, or at least start conveying to you, that turbulence, magnetic fields, cosmic rays are important for galaxy formation. And this is not something which many people will pay attention to, but please do pay attention to. And I wanted to ask how and when the first fields arise, and the turbulent dynamos are required to maintain fields. The field coherence, when this random stretching saturates, is something which is still an unsolved problem, but the amount that we have looked at it, it looks as if you do get coherent enough fields to explain observations of random Faraday rotation in galaxy clusters. For large-scale dynamo, an issue which I have not had time to talk about is magnetic helicity conservation. But I have kind of indicated to you that these fluctuation and large-scale dynamos go together. It turns out the large-scale fields grow rapidly as the tail of the small-scale dynamo in the beginning, and then continues to grow as small-scale saturate. And for the first time, we are seeing signs of both these dynamos. I have not really had time to mention anything about the early universe. Is it needed? Is it inevitable? It's not needed, but if it is there, it could be pretty interesting and change various aspects of even structure formation if there's a primordial field which is generated. There are very interesting probes of all this stuff. The first probe, of course, is radio astronomy, and those are the images that you saw there. And that's the traditional probe. And the SKA, when it comes online, it's one of the key projects is origin of cosmic magnetism, which will continue to be interesting. There are very unexpected probes from gamma ray astronomy, which are trying to tell us that there are maybe intergalactic magnetic fields of very small strength. And if you are producing things in the early universe, gravitational wave astronomy will also be interesting, because for space-based the gravitational wave detectors like LISA, or for the pulsar timing array, you will get various interesting signals apart from the CMB, of course, which was already mentioned. So let me stop. Thank you for the attention.
We have time for questions.
Hi. So in the simulations, do you also track the electron density of the plasma?
This is all assumed. In these simulation, everything is assumed to be ionized. But you can track if you have neutral component and ionization equation, you can solve it also. The solar guys, especially near the surface, they would like to track the ionization part of it. Here, everything is assumed to be ionized. So the electron density follows the total density. For incompressible stuff, it's kind of more or less uniform, or whatever you assumed in the beginning. For the compressible simulation, there'll be shocks where it will get enhanced.
So what I was basically asking is, like, is there a way we can understand the turbulent magnetic field and the turbulent electron density?
Turbulent electron density, you mean?
At the very small scales, if I have turbulence, and can I understand the origin of the turbulent magnetic field in terms of these turbulences? No.
I mean, you are saying from plasma effects. Plasma effects typically produce fields on the scale of the skin depth, ion skin depth, or plasma scale, which are all very small. To get it to these large scales, it involves a lot more effort. I don't think it's possible, but it may be, I mean, you have to think more if you want.
Thanks.
More question?
So turbulence kind of transfer power from large scale to small scale, and that's something you showed, like the power spectrum increases at small scale. Is it too far-fetched to think about that when we'll measure the power spectrum at large scale, will the magnetic field effects will be seen and turbulence and magnetic field effects will be seen at some point? Like, can it dominate and impact the large scale power?
You mean in structure formation?
In structure formation, yes.
No. In all the systems that one has observed the magnetic field, for example, in the interstellar medium of our galaxy, it is comparable to the turbulent pressure the interstellar medium pressure. In galaxy clusters, it is subdominant to the thermal pressure. Otherwise, you won't be able to measure the mass of clusters. So it will not dominate there, but if you have a primordial field, for example, if you produced an early universe field, it could, because the Lorentz force is J cross B, and J has one more K. So even if you produce fields in a scale invariant way, you will find that the power spectrum of density fluctuations in the batteries at small scales is dominated by the Lorentz force if the field is strong enough. And the fields which have, right now, there are limits on the field strength. From the CMB, there is about, at the best, 0.1 nanogauss as redshifted to today. The field has to be smaller than that. From the gamma ray, they think the field has to be stronger than 10 to the minus 16. A big room there. If the field is on small scales, yes, it can affect the first structures which form. And we have written papers about reionization getting affected, the signals in 21 centimeter. There's a big game, very interesting game you can play at that end, which we can discuss.
Right, let's thank the speaker one more time.